Now, we have already solved four numericals. You can see in my previous videos. Now, this numerical number 5 says that a ball bearing. Remember, I have always told you that if it is a ball bearing, then A or P, right? Remember the load life formula? The load life formula is L10 is C upon PE raised to A. In some books, this is written as P. So whatever this A or P is, if it is ball bearing, you're going to take the value as 3. And if the bearing is a roller bearing, then you are going to take the value of A or P as 10 by 3. So first value, we understood that A we are going to take as 3. Has a radial load, right? You know that radial load is denoted by FR, right? And we always convert the load from kilonewton to Newton. So 5 kilonewton, the load will be converted as 5 into 10 raised to 3 Newton. So 5000 Newton is the radial load. So given data is ball bearing and radial load and expected life for 90% bearings. 90% bearings is L10. And since the bearing life is given in hours, so L10H is given. If L10 is given, it would be in million revolutions. And if L10H is given, then the life will be given in hours. So here it is in hours. So L10H is given. And that too here, the value of L10H is 8,000 hours. What would be the dynamic load capacity, dynamic load rating, whatever the word is used, that is C. So we are told to find out the dynamic load carrying capacity C. When the shaft the shaft is rotating at small n, which is 1450 RPM. So n is given 1450 RPM. So we have to find out C. The first thing, obviously, we do not have our equivalent load. So we will first find out equivalent load. Before that, our life is in hours. So we are going to convert it into million revolutions, right? So let us start the first formula. We are going to convert our life from hours to million revolutions, right? So the formula is 60 into n into L10H upon 10 raised to 6, or L10H into 60 into n divided by 10 raised to 6. It's one and the same thing. Some books it's written in this way, somewhere it's written in this way. So obviously the value of L10H is 8,000, right? The value of N you can see here, that is 1440. So once you do the calculation in your calculator, you will get the answer as 696 million revolutions. Life of bearing at 90% reliability, L10, right? Or L90, whatever you say, that is 696 million revolutions. Now, let's move ahead. On page number 15.2, I have discussed in previous numericals also, this formula is there. XVFR plus YFA into S, where X is radial load factor, V is race rotation factor, FR is radial load, Y is axial load factor, FA is axial load, and S is load application factor or service factor. Only X value is given. V is not given, we will take it as 1. Only FR value is given, sorry. X value is not given, we will take it as 1. FR value is given. Y value, we don't need. This whole axial load is not given, so we are going to assume it nothing. It's 0, right? S value is not given, we are going to assume 1. So ultimately, our equivalent load will be equal to radial load. So our radial load is our equivalent load, which is 5000 Newton. Axial load is not given, right? Inner race is rotating. We assume V as 1. X we are going to assume 1 because it is a purely radial load. So obviously X will become 1 since it is a purely radial load. No shock load condition. We are going to assume S as 1. So we found out PE as FR, which is 5,000 Newton. Moving ahead, now we just have to use this formula of L10 is C upon PE raised to 3. Now, we found out that L10 is 696, right? When 3 wants to come here, simple mathematics, it will become 1 by 3, right? T, which is 5,000 Newton. So from here, when it will go here, it is going to be multiplied. So into 5,000 is equal to our dynamic load carrying capacity. So our dynamic load carrying capacity, when you do these calculations in your calculator, you will come to know that dynamic load carrying capacity is 44310.48 Newton, right? So very easy and the most simple numerical. Now, I'll share the screen again. We have finished with the 5th numerical. Let's go with the 6th numerical, right? So now up till now, we did the numericals on ball bearing. Now this is the first numerical that we are doing, which is on roller bearing. Remember, whenever roller bearing is there, A we are going to take as 10 by 3. I told you in load life relationship, L10 is load, L10 is life, P and C are our loads. So L10 is C upon PE raised to A. A we are going to take it over here as 10 by 3. So you have to read the numerical carefully, whether it is roller bearing or it is ball bearing, and accordingly you are going to select the value of A. Dynamic load capacity, this time directly C they have given, which is 26,000 Newton. This time C is already given. If the desired life L10, but it is also in hours. So L10H, 90% bearings. So L10H is given, which is again just like the previous value, 8,000 hours. The speed is 300 RPM. So the speed is 300 RPM, N is 300 RPM. This time we have to calculate the equivalent radial load, which is FR. Again, see guys, our formula is PE is equal to X V FR plus Y FA into our load application factor or service factor S. Since they have told us to find out equivalent radial load, nothing they have mentioned about axial load. So this whole factor will become 0. They have nothing mentioned about our load condition, whether it is shock load, no shock load, mild load. So we will assume no shock load condition. So we will assume S as 1. Nothing about race rotation factor they have mentioned, whether inner race rotates, outer race rotates. So we will assume 1. Inner race rotates. It is so again the load will become purely radial load. So we will assume X also as 1. So in this numerical also P is PE, equivalent dynamic load, will be equal to purely radial load or equivalent radial load, which is FR. So let's start. First, we are going to convert our life from hours to million revolutions. So let's start. So you can see here L10 million revolutions is L10H. So we'll put down the value of 8,000. N RPM, it is given 300 RPM. So we will put the value of N as 300 divided by 10 raised to 6. So L10 you will get as 144 million revolutions. Next, I'm going to use the formula of load life relationships. L10 is equal to C upon PE raised to A. Here A is going to be 10 by 3. So again, L10 is there with us, which is 144 is equal to CE we have as 26,000 divided by PE. If 10 by 3 goes this side, it will become 3 by 10. Obviously, PE will go here and 144 by raised to 3 by 10 will go down. So formula will become PE is equal to 26,000 divided by 144 raised to 3 by 10. 3 by 10 becomes 0.3, right? So 26,000 divided by 144 raised to 0.3, your answer will come 5854.16 Newton. So our PE is equal to FR. So our radial load will become 5854.16 Newton. So again, a very simple numerical was there regarding the roller bearing. This was the first numerical that we did regarding roller bearing. Sixth numerical is completed. Let's go to seventh numerical. Numerical number 7 says, find dynamic load carrying capacity. So obviously they are telling us to find out C. What is the dynamic load carrying capacity? Dynamic load carrying capacity, if a deep groove ball bearing, again it's a numerical of ball bearing, so A will become 3. I told you our formula of load life relationship is L10 is C upon PE raised to A, where A is ball bearing. So we will take the value of A, or in some books it is written as P. For example, in Bhandari Design Data book, this A is mentioned as P. So whether we write down A or whether we write down P, it's one and the same thing. So P or A is going to be 3 because it is the numerical of ball bearing. Moving ahead, let's read what else is given. Radial load of 4,000 Newton is given. So FR is given 4,000 Newton. Axial load, sometimes it is also called as thrust load. So FA is given as 5,000. FR was given as 4,000. Operating at 1600 RPM, small n. RPM is given as 1600. For average life of 5 years at 10 hours per day. 5 years at 10 hours per day, assume uniform and steady load. So see guys, S or K, application factor KA or service factor S, whatever you say, its value you have to assume on the basis of uniform and steady load. How to select? I'll tell you. So let's move. Let's very quickly write down. Now, see guys, first, we are going to assume 5 years. See, 1 year has 365 days. But every day we won't work. Holidays, Sundays, if we remove them, then we will assume that we are working for 300 working days per hour. Right? So, now we can find out our L10H in hours, as we are working for 5 years. The life of this bearing, single row deep groove ball bearing, is 5 years. But in a year, we are working for 300 days, and that too 10 hours per day we are working. So 5 into 300 into 10, the answer turns out to be, do it in your calculator, 5 3s are 1500 into 10, 15,000 hours, right? The rest given data I have written here. For example, radial load is FR, axial load is FA, NRPM is 1600. This whole calculation I have done here, right? Now, one thing that should be noted is that we do not have our X and Y. which is our radial load factor and axial load factor. Suppose we assume here nothing is mentioned regarding V, race rotation factor. Previously also I have told you, we will assume race rotation factor V as 1 if inner race rotates, and we will assume V as 1.2 if outer race rotates. Here it's not written outer race rotates, so we will assume V as 1, that is inner race rotates. Right? So how to find out the value of X and Y? We are going to find out the value of X and Y from PhD design data book. If you are using, you should refer page number 4.4. But particularly in this video, I'm solving all the numericals of Bhandari design data book. Then in Bhandari design data book, table number 15.9, you have to refer. And that table is regarding X and Y factors for single row deep groove ball bearing. See guys, we are solving the numericals of single row deep groove ball bearing. So we will use the table for single row deep groove ball bearing. How to find out the X and Y value? By the way, this is on the page 15.2 of Bhandari design data. How to find the value of X and Y? See, there are these values are there. Then how to find them? First, we will calculate FA upon FR, or say VFR. First, we will calculate FA upon VFR. This ratio, V is 1. So obviously, we will find FA upon FR. And then we will check whether its value is greater than E, that is 0.44, right? Which is this condition. Or it is less than or equal to E, which is this condition, right? So let's start. First, let us find out the value of FA upon FR. So FA upon FR, 5,000 upon 4,000. The value turns out to be 1.25. Now, obviously, if you compare 1.25, then it is greater than this E value, which is 0.44. So I can say that this FA upon FR, which is 1.25, is greater than E, which is 0.44. So we are going to select this table for selection of our X and Y. Right? So if you see this table, already you understand that everywhere X is 0.56. So we already found out our X value, which is 0.56, but Y value is changing. So if Y value is changing, the next thing you have to do is that you have to find out FA upon CO, right? So if you see here, the value of the CO, static load carrying capacity, is not given. CO is, sorry, I just got a phone call, so I had to just, okay, I'm again getting a call. I'll disconnect quickly. So yes, so guys, I was saying that CO is not given, but if CO is not given, we will take its larger value, FA upon CO, because we have to do this. So FA upon CO, since we cannot calculate FA upon CO, let's take the last line and let's take these values of X and Y. So X is 0.56 and Y is 1. Right? Suppose if FA upon CO value was 0.13, then this is the 0.13 line, then Y we would have taken 1.4. But here we don't have CO value. We cannot do this ratio as FA upon CO. We cannot do its calculation. Then let's take this last line, because our FA upon FR is greater than E. Our E value is this. So we will take the last line, which is 0.500. And that's why our Y value will be 1, which is seen here. I'm highlighting it very badly. Y is 1. So now we found out X as 0.56, Y as 1.0. Now we should proceed with our calculation. Simple PE, equivalent load formula, right? X we right now found out, which is 0.56. Race rotation factor, we assumed as inner race is rotating. So we took as 1. Radial load is given. You can see here FR, that is 4,000. So radial load is already given in the numerical. Y we found out from this table from here. So Y is 1. Axial load is given, right? You can see here FA, axial load is given in the numerical 5,000, right? So 7240, what is the value of S? How much to assume? Since they have mentioned in our numerical, I'll tell you. But PE from Bhandari Design Data Book, your formula XVFR plus YFA, that is 7240. Now, in numerical, it is said that uniform steady load. So from this type of service, uniform steady load, S, that is your service factor, or KA, that is your load application factor or load factor, turns out to be 1. But in some books, uniform steady load is also taken as 1.2. So if you take it as 1, your PE will be 7240 Newton, right? But if you take it as 1.2, right, then you will have to multiply this 1.2 with this 7240 Newton. So 7240 into 1.2 turns out to be 8688 Newton. Your equivalent dynamic load is 8688 Newton. We have found out P. Remember our formula? L10 is C upon PE raised to A. In some books, this is written as P. In some books, it is also written as say K, but the value is 3. We have found out this. We should find out this because we have to find out this. That is dynamic load rating. So let's do it. You can see here, our life is given as 300. It is given for 5 years, 10 hours per day. We assumed that in a year, 1 year, working days are going to be 300 working days. So 15,000 hours. We have found out this. So life is in hours. Life is in hours. We have to convert it into million revolutions. So the formula is again there in Bhandari Design Data Book. L10, LH10 into 60 into N divided by 10 raised to 6. This is 15,000 hours. Life in hours, 60. RPM is given 1600, right? So RPM is given as 1600 here in the given data. So now we are just going to do the simple calculation, which is 15,000 into 60 into 1600 divided by 10 raised to 6. It turns out to be 1440 million revolutions. Now we are going to use our formula of load life relationship, which is L10 is C upon PE raised to A. In some books, it is K. In Bhandari, it is P, right? But it is nothing but 3 for ball bearings and 10 by 3 for roller bearings. Now it is not a numerical of roller bearings. It is a numerical of ball bearings. That's why we are going to take it as 3. We right now found out our PE as 8688. Our L10 we found out as 1440 million revolutions. When 3 will go this side, it will become 1440 raised to 1 by 3. And 8688 will go and get multiplied over here. So 8688, you will get C, and that turns out to be this much. You should go to design data book, and in front of this much load carrying capacity, you should be selecting a proper bearing or higher than this much basic dynamic capacity, either this much or higher than this. Whatever C value comes out in front of that, whatever value of SKF bearing is written, that you are going to select. So it's very easy numerical. Guys, if I would have taken S as 1, remember our numerical PE, remember our equivalent load, right? Equivalent load is XVFR plus YFA into S. If I assume this S as 1 as per that table, then this PE would have been 7240. Then here I would have written 7240. So now the answer would be 1440 raised to 1 by 3 into 7240, right? And whatever the answer comes on your calculator, that would be the basic dynamic capacity. So selecting your application factor on basis of that, your answer of C has changed. It was a very easy numerical, and don't forget, it was asked in your exam. Let's move on to another numerical. Roller bearing. See, now this numerical is on roller bearing. Subjected to radial load, FR. Radial load is given 5000 Newton. Desired life at 90% reliability, L10. 90% reliability means L10. And since it is given in hours, so L10H. Right? So L10H is given as 15,000 hours. FR, radial load, FR is given as 5000 Newton. What else they are telling us to do? Let's find. They are saying that load application factor KA or S, load application factor, whether you write down KA or whether you write down service factor S, it's one and the same thing, right? So load application factor, they are telling that it is 1.5. Shaft RPM, N, small n, 1440 RPM. Calculate the required dynamic load rating. If you say basic dynamic load carrying capacity, or if you say basic dynamic load rating, it's one and the same thing. So C. Let's find out. Let's first write down the given data. It's a roller bearing, right? So our A or P or K, whatever you write down, that is going to be 10 by 3 this time. In your formula of life load relationship, here, this A or P or K, whatever you say, that is going to be 10 by 3. Radial load is given, no axial load, purely radial load, right? So whenever there is purely radial load, your radial load will become equivalent load, right? Because if we see the formula, right? If you see the, just a second, let me erase these things. I can show you properly. It's purely radial load. So X we assume as 1. Axial load is not there, so Y we will assume as 0. So in this whole formula of PE, which is XVFR plus YFA, PE is equal to XVFR plus YFA. Axial load is not at all given, so this whole thing will become 0. Purely radial load, so X will become 1. Nothing about inner race or outer race is given, so we will assume inner race rotates, right? V as 1, right? Then multiplied by S or Ka, which is 1.5, right? So we will do that calculation as PE is XVFR plus YFA, and 1 into 1 into 5,000 into 1.5, 7500 Newton. Now see guys, L10H is given again 15,000 hours. N is 1440 RPM. So the answer will be 1296 million revolutions. Again, since we want to find out C, we will use this load life relationship or life load relationship. L10, we just now found out 1296 million revolutions. PE, we just now found out as 7500 Newton, right? So if you see this, when this 10 by 3 will go here, so it will become this way, 1296, 3 by 10 multiplied by 7500 will go here. So it will become 7500 is equal to C. So C value will be 64393.61 Newton. So this numerical, 8th numerical, we are done with, right? Let's go with the 9th numerical, which was asked in the winter 18 examination, university examination. Deep groove ball bearing. Again, ball bearing, right? So our A or P, whatever you say, that is 3. Rated static and dynamic load capacity. Static load capacity is CO. Dynamic load capacity is C. So they have given CO as 4150 Newton and C as 4750 Newton. Axial load, they are giving us FA, right? Axial load is 2075 Newton. Radial load is FR is 4000 Newton. Find the expected life of the bearing, L10. Expected life at 90% reliability. Whenever the reliability is not mentioned, by default, you're going to assume at 90% reliability. So 90% is L10, right? So L10 life in million revolutions you have to find. Let's start. X and Y values are not given. So this numerical, particularly, we have to choose X and Y value from the table of deep groove ball bearing. And we have to find out value of X and Y. So let's see how we have to do. Let's write down first the given data. You can see here the static load capacity CO is 4150 Newton. Dynamic load capacity is 4750 Newton. Axial load is 2075 Newton and radial load is 4000 Newton. So whatever values were given, we have already written down. In order to determine these two factors, let us go to the table, right? The table is here. So obviously in this table, we need to find out FA upon CO and FA upon FR. So then we can find out FA upon FR. Then we can find out the value of X and Y. So let's go. Since we need to find out FA upon FR and FA upon CO, you can see FA is 2075. FR is 4000. So the answer is 0.51. FA is again 2075 and CO is 4150. So that also turns out to be 0.5. So FA upon FR is 0.51. FA upon CO is 0.5. Now, what we will do, we will go to our table and check. FA upon FR, we found out as 0.51, which is higher than the value of E, right? Our FA upon FR value is 0.51, which is higher than the value of E, higher than this E value, which is 0.44. So we are going to see this table, not this table. But how to find out? X we will find out. It's common. X is 0.56. Now that we understood. But what about Y? For Y, we will see FA upon CO. So let's see. So FA upon FR we found out. We found out that it is greater than 0.44. FA upon CO is exactly 0.5. Right? You can see here. FA upon CO is exactly 0.5. So we are going to select this value in front of 0.5, whichever Y value is there, 1, that is what we are going to select. So X is 0.56, Y is 1. If FA upon CO would have been 0.250, then Y we would have taken as 1.2, but here it is 0.5. So that's why we are taking Y value as 1. So that you should understand properly. We are still going to do many more numericals like this. You can see my previous videos also and upcoming videos also. So there you will be able to understand how to do, but this is very simple, right? First, you have to compare with E, FA upon FR, you have to compare with E, and then you will get X as 0.56. Then for Y, we usually see FA upon CO, and since here FA upon CO is 0.5, so in front of that value, Y value is 1, so we have taken X as 0.56 and Y as 1. Moving ahead, now we can, nothing is mentioned regarding the load condition. So we will take as no shock load and we will assume S or KA, application factor, or S is the service factor, shock load factor. We will consider that as 1. Moving ahead, PE, numerical formula on page number 15.2. By the way, this table which we saw is on page number 15.6. Which table you should see? Single row deep groove ball bearing, because this numerical is of single row deep groove ball bearing. So this table you have to refer from Bhandari design data. Moving ahead, guys. Our formula is PE is XVFR Y FA into S or KA, whatever is there. S or KA, we assumed 1 because it is shock load condition. X we right now found out from the table as 0.56. Nothing is written. Inner race rotates, outer race rotates. We will consider inner race rotates. Assuming that, we will take V as 1. Radial load is given 4,000. Y we found out from the table as 1. Axial load is given 2075. So our answer is 4315 Newton. Very easy. Equivalent load is found out. Very quickly, let's go to the rating life. Right? See guys, in numerical itself, see dynamic load carrying capacity values given 4750. PE, we right now found out as 4375. And this numerical is of ball bearing. Ball bearing value is always 3. When you do the calculation, you will get the answer as 1.339 million revolutions. Let's go to the 10th numerical. 2 times it was asked in university exam. 2 times. Very important. Single row deep groove ball bearing number 6002. Bearing number 6002. The CO value is 2500 Newton. That is static load capacity is 2500 Newton. and dynamic load capacity C is 5590 Newton. So you can see static load capacity CO is 2500 Newton. Dynamic load capacity C is 5590 Newton. Thrust load, axial thrust means FA, that is 1000 Newton. And radial load is given. Radial load, how much? The radial load is given 2200 Newton. Find the expected life of 50% bearings. Up till now, we were doing at 90% reliability. 50% reliability means you have to find out the life when the 50% bearings have failed and 50 was still working. So at that condition, you have to find out the life. It's very easy. Let's start. So first thing you can notice is that in this numerical, X and Y values are not. See, one way you can see is that if it is written purely axial load, then remaining thing will become all zero and radial load will be equivalent load. But here they have not written purely axial load. Means you have to find out the value of X and Y. So read the numerical properly and you will come to know what you should do. So we have FA, we have CO. We have FA, we have FR. So we can find out FA upon CO ratio, FA upon FR ratio, and see whether it is FA upon FR is less than E or FA upon FR is greater than E. And accordingly, we can see our table. So let's do the calculation. FA upon FR. First thing is FA is 1000. FR is 2200. So we found out as 0.555. But again, this 0.555 is more than 0.455 E value, right? So I'm trying to say is that this ratio is greater than this E value, which is 0.44. Hence, this condition is satisfying, right? 0.455 is greater than 0.44. So FA upon FR is greater than E. So yes, we are going to see this table. So now one thing is sure that X is going to be 0.56. Once we understood that FA upon FR is greater than E, X value is 0.56, that we understood. But what about Y value? For Y value, we are going to see FA upon CO. Interestingly, FA is 1000 and CO is 2500. The ratio comes out to be 0.4. Interestingly, I use the word interestingly because the 0.5 lies between 0.250 and 0.500. So this value of Y also will lie between 1.2 and 1.0. So that we are going to find out from interpolation method. Let's see how you should do, right? So like I said, X value is known, but since our 0.4 lies between 0.250 and 0.500, so our Y value will also lie between 1.2 and 1.0. So let's write down that in this way, that for FA upon CO 0.250, Y value is 1.2. And for 0.500, FA upon CO 0.5, Y value is 1. You can see here, Y value is 1. Then for FA upon CO, which is 0.4, what will be the Y value? That we have to do it by interpolation, right? How to do it? By interpolation. Name this as X1, this as Y1. Name this as XR, this as YR. Name this as x2, this as y2. Then use the formula as y1 minus yr upon x1 minus xr is equal to y1 minus y2 upon x1 minus x2. Put all these values of x1, xr, y1, right? Yr you are going to keep just as yr. Put the value of y1, y2, x1, x2, and simply you just have to put these values in this formula and you will get the value by this calculation as 1.08. So y value is 1.08. You'll have to use your calculators in that formula and you'll get the value as 1.08. Here is the formula. Now, obviously, if I write down y1 minus yr upon x1, x, or this side and this side, nothing is going to change. It's one and the same thing, right? So, y value we found out as 1.08, or in short, this yr value we found out as 1.08. Now, simple. Next thing is very easy. We are going to use the we are going to use the formula of equivalent load, which is on page number 15.2 of Bhattari Design Data Book. XVFR plus YFA. Nothing is mentioned whether inner race rotates, outer race rotates. So we will assume V is equal to 1. Inner race rotates. V is equal to 1. Right? Nothing is mentioned regarding the load. So we will assume this S or KA as 1. Right? So just putting the value as X we found out as 0.56, Y we found out as 1.08, FR is given in the numerical 2200, FA is given in the numerical 1000. You'll get the answer as 2312. Next, you're going to use the formula of load life relationship. L10 is C upon PE raised to A or P or K, whatever you write down. That's also on page number 15.2 of Bhandari Design Data Book. L10, right? We have to find out. We have C, right? C is already given in the numerical as 5590, right? PE, we just now found out, which is 2312 raised to 3. We will get the value of L10, which is 14.13 million revolutions. So very easy. L10 we found out. Now they have not told us to find out life at 90% reliability. They have told us to find out at 50% reliability. Whenever 50% reliability is given, remember 50% life at 50% reliability is 5 times the life at 90% reliability. I'll repeat. Life at 50% reliability, L50, is 5 times the life at 90% reliability. So you just have to do this. L50 is 5 times L10. Simple. So 5 into this 14.13, you found out the life as at 50% reliability as 70.65 million revolutions. That means when 50% bearings were rotating and 50% failed, at that time, the life of that group of bearings was 70.65 million revolutions. That is what the practical meaning is. So we have done 5, 6, 7, 8, 9, 10 numericals, many more to go. But for now, we will stop here. For the other next numericals, you can refer to my next video. Thank you for watching.